Hello everyone. So my name is Zakariya. I'm from the Mohamed 5 University from Morocco. I work in collaboration with Professor Chantal from University of Lyon and Professor Sherifi from this university. So the subject of this presentation is the characterization of the relationship between the overlapping nodes and the highly connected nodes in a network. So in real-world networks, the majority of nodes are organized into densely connected nodes. In fact, there is two types of communities. The non-overlapping community structure where nodes can belong only to just one community, and the overlapping community structure where nodes may belong to multiple communities, and these nodes are called the overlapping nodes. So, for instance, in a social network, the individuals can belong to multiple groups, such as family and work and so on. Real-world networks are also known to exhibit a heavy-tail degree distribution, where the majority of nodes have few links, and some nodes have a large amount of interactions, and these nodes are called the hubs. So our objective in this talk is to study the relationship between the overlapping nodes and the hubs, because this will give us a new perspective on how the communities are organized. So in this work, we suppose that the overlapping nodes are neighbors with the hubs, and to verify this property, we follow this methodology. So at first, we define the community structure of our real data sets using a given community detection algorithm. Of course, if we don't have ground truth data. After that, we try to define the ego network of overlapping nodes. And this network is formed from the immediate neighbors of the overlapping nodes. And we define also the list of hubs. So in order to compare the list of hubs with the list of neighbors of overlapping nodes, we perform some evaluation measures. So we perform the proportion of hubs, the rank biased overlap. We also measure the correlation between both lists, and we analyze their degree distribution. So as I said before, the ego network is formed only from the immediate neighbors of the overlapping nodes. So after obtaining this network, we can now define the list of neighbors of overlapping nodes. While the list of the hubs is defined by sorting all the nodes of the network according to their degree. So, and the list of hubs is defined as the most the top nodes, such that the list of hubs and the list of neighbors of the overlapping nodes have the same size. So in this work, we perform a series of experiments on different real-world data sets coming from multiple domains. These networks are classified according to their size. So in small networks, we use the Karate Club network, Les Misérables, Dolphins, and Game of Thrones. In medium networks, we use Echo Facebook and Quantum Cosmology Collaboration Network. And finally, in large network, we use high energy physics, condensed matter collaboration network, and finally, Enron email network. So the first small network is Karate Club. It's a social network where nodes represent the members of Karate Club, and the links represent their friendship. So this network has a relatively high density and a negative assortativity. Les Misérables is a co-appearance network where nodes represent the characters of Victor Hugo's novel. And a link between two characters exists if the two characters appear in the same chapter. This network has relatively high density and negative assortativity. Dolphins is another social network where nodes represent dolphins and edges represent the frequent association. This network has also a relatively high density and a negative assortativity. And the last small network is Game of Thrones network, where nodes represent the characters of Game of Thrones series, and the links exist between two nodes if they appear in the same line. So this network has also a relatively high density and a negative assortativity. So for medium network, we have Ego Facebook. It is a social network where nodes represent the Facebook profiles and the edges are Facebook friendship. So this network has a small density and a positive assortativity. And Quantum cosmology is a collaboration network where nodes represent authors and links are their co-authorship. This network has a small density and high assortativity. And concerning the large networks, they all have a very small density and they are all assortative except for Enron email. So the first measure that we use is the proportion of hubs. This measure quantifies the percentage of hubs belonging to the echo network of overlapping nodes. So it is equal to the intersection between the list of hubs and the list of neighbors of overlapping nodes. So if we consider this toy example, so we have the list of neighbors of the overlapping nodes and the list of hubs. They share the 7 first elements and they have a different 2 last individuals. So the proportion of hubs in this case is 7 divided by the size of the list, which is 8. So it is equal to 87%. So before performing this measure on our real-world data sets, we first define the community structure using the speaker-listener label propagation algorithm. So here is the bipartite representation of our small networks. So where the overlapping nodes represent the left column of this graph, and the middle column represents the hubs, and the right column represents the rest of the nodes. So as you can see, the overlapping nodes are neighbors with the majority of the hubs, and this can be confirmed by the value of the proportion of hubs, which is equal to 77.6% for Karate Club and 81% for Les Misérables, and 77.8% for Dolphins and 67% for Game of Thrones Network. And it has also high values in medium and large networks. So where the hubs represent more than 50% of the nodes belonging to the echo network of overlapping nodes. So the second measure is similar to the last one, but it is called the rank biased overlap. It quantifies the intersection between the list of neighbors of the overlapping nodes and the list of hubs, while incrementally increasing the depth of both lists. So and the overlap of each depth has a different weight. The weights are set by the parameter p. So when p has a small value, more weights are given to the first elements of both lists. The rank biased overlap is ranging from 0 and 1. It is equal to 1 when both lists are similar. So according to the results here, the rank biased overlap has very high values, and it has even higher values when p is equal to 0.5. In this case, more importance is given to the first elements of both lists. So we can conclude from these experiments that the list of neighbors and overlapping nodes and the list of hubs are very similar. we use also Pearson and Spearman correlation coefficients in order to measure the monotone relationship between the lists of degrees and the lists of ranks of neighbors of the overlapping nodes and hubs. And the results show that both coefficients have very high values. They are very close to 1. So we can conclude that there is a very strong monotonic relationship between both lists. After that, we analyze also the degree distribution of both lists. So, and this for medium and large networks. So we notice from the results that both lists have exhibit a heavy tail degree distribution. We also represent their estimated degree distribution under the power law hypothesis, and the results show that the exponents are very close. So if we take the example of N1 email, the exponents is equal to 2.41 for the list of neighbors of overlapping nodes and 2.39 for the list of hubs. So we can conclude from these experiments that both lists have a power law degree distribution with very close exponents. After that, we also study the influence of the neighborhood of the overlapping nodes. And this is for all the different type of networks. So we represent in these tables the proportion of hubs while increasing the size of the echo network of the overlapping nodes. So the results show that the proportion of hubs increases while increasing the size of the ego network of overlapping nodes, and this is totally normal because when we have a large ego network, so there is more chance that it may contain more hubs belonging to different communities. We also study the influence of the membership degree of the overlapping nodes. So we represent in this table the proportion of hubs as a function of the membership degree of the overlapping nodes. So results show that for all the different networks, the proportion of hubs increases while as the membership degree became higher. This is because when we have an overlapping node with high membership, it belongs to several communities, so there is a very high chance that is neighbor with more hubs. In the second part of our experiments, we try to compare the global or the original network with the overlap hub network. For this end, we define first of all the community structure of the real world networks. After that, we try to define the overlap hub network, which is formed only from the overlapping nodes and the hubs. And in order to compare this network with the original network, we perform some network properties, such as the average and the median distance. So here is an example of the overlap hub network for Karate Club. As I said before, it contains only the overlapping nodes and the hubs, and we removed all the other nodes of the network. So in this experiment, we represent the average and the median distance of both the overlap hub network and the global network. So for those of you who don't know the difference of the distance, it is simply the shortest path between two nodes. So the distance of the overlap hub network will tell us how much the hubs are close to the overlapping nodes, and it is equal to 1 when we have each overlapping node is neighbor with all the hubs. So we can notice from the results that in small networks, the average and the median distance of the overlap hub network are slightly lower than the ones of the global network. This is because the small networks have a high density, so even if we consider the entire network, the nodes are still very tightly connected. So that is why the values of the average and the median distance of the overlap hub network are very close to the ones of the global network. And in medium and large networks, we have the distance of the overlap hub network are very small as compared to the same measures for the global network. So we can conclude that in this case that the overlapping nodes are tightly connected to the hubs as compared to the other parts of the network. And in conclusion, in this work, we tried to characterize the relationship between the overlapping nodes and the hubs. For this end, we used different empirical networks from different domains and sizes. At first, we compared the list of neighbors of the overlapping nodes and the list of hubs. So we used some measures such as the proportion of hubs, the rank biased overlap, and the correlation. And we found that they all have very high values, and we also analyzed their degree distribution, and we found that they both exhibit a power law degree distribution with very close exponents. And in the second part, we tried to compare the overlap hub network with the global network, and we used the median and the average distance. And we found as a conclusion that the distance of the overlap hub network is very small as compared to the distance of the global network, namely for the medium and the large networks. So in the next step of our work, we will try to perform the same measures using another community detection algorithm in order to confirm this our hypothesis. So thank you for your attention.
Thank you. So questions? Well, it was, you mentioned, in fact, the question I had in mind. All this seems possibly very related to the method you use to perform overlapping community detection. So, yes. Have you a comment on this?
No, it's as I said, it is it is our next step. We will launch another.
And have you some intuition of why such overlapping nodes are neighbors of hubs? Is there some intuition behind that? Because if you did the job, you had some reason. So what was your original motivation? Our
original motivation it was based on a work of one colleague who is working with our team. He tried to develop a new immunization strategy, but by immunizing randomly one of the neighbors of the overlapping nodes, and he finds that this measure correlates strongly with the degree distribution, with the degree-based immunization strategy. So he had the assumption that the overlapping nodes can be neighbors with.
Okay, so we confirm this.
Yes.
Any question again? No. Maybe just one last question. If you perform link communities detection, you have obviously overlapping nodes. So did you think of of doing this kind of thing? Because, in fact, non-overlapping communities, it's a thing a bit strange in graphs. So, in networks, in my opinion. So there are various ways to have overlapping nodes, but one of these ways, which is rather popular, is to try to partition edges rather than nodes. Have you some idea or project on this slate?
Actually, I didn't.
No, not yet. Okay. Anyway, thank you very much.